Hello students, welcome back to our class. Now in this module we are going to discuss about objective type questions which were given in the real numbers chapter. So these are direct one word questions. You can directly answer them. Every positive even integer is of the form 2q. Then every positive odd integer is of the form dash. See, if 2q gives an even number, 2q gives an even number, it means for any value of q belong to any natural number. Q equal to 1, 2 into 1 equal to 2. Q equal to 2, 2 2s are 4. Q equal to 3, 2 3s are 6 and so on. What are these 2, 4, 6, 8 and so on? They are all even numbers. So that is why 2q is called the standard or general form of even numbers. Then what is the general form of odd numbers? See, even number minus 1 or plus 1 can be odd number, right? Even number minus 1 or even number plus 1 can be an odd number. So every positive even integer is of the form 2q, then every positive odd integer is of the form where q is some integer. So that even plus 1 or even minus 1 can be an odd number. Therefore, what is the standard form or general form of odd number? Every odd number is of the form 2q plus 1 or 2q minus 1. So this is what is the standard form of odd number. So that your answer is going to be 2q plus 1 or 2q minus 1. You better write 2q plus or minus 1. Clear? Coming to the next one. The exponent of 2 in the prime factorization of 144. So for that you will have to factorize this 144 as the product of primes in a unique way. So 2 times 7s are 14, 2 2s are 4. Okay, and again 2 into 2 into 2 3s are 6, 2 6 are 12. Again 2 into 2 into 2 into 18 is 36. Again 2 into 2 into 2 into 2 into 9. So 1, 2, 3, 4. Can you write it as 2 to the power of 4? And 9 can be written as 3 square. So 2 power 4 into 3 square. But what are you asked? The exponent of 2 in the prime factorization of this. What is the exponent of 2 here? That is 4. So your answer is going to be 4. Because you are asked only the exponent of 2 in the prime factorization of 144. Coming to the next problem. Every point on the number line corresponds to a dash number. See, this is a real number line. And what kind of number line that is? That is particularly called as a real number line. So on this real number line, this is 0, and you can express root 2 also on the number line. You can express 1 on the number line. You can express 1 by 2 on the number line. You can express 1 by 3 also on the number line. So what are all these numbers here? All these numbers are real numbers. Therefore, every point on the number line corresponds to a real number. What kind of number that is? A real number. Next, coming to the product of three numbers is dash to the product of their HCF and LCM. Let us consider three numbers. I am going to take three numbers. For example, 1, 2, 3. These three are three numbers. What is the product of these numbers? Product of these three numbers is equal to 1 into 2 into 3. 1 times 2 times 3 is equal to 6. That is the product. And what is the product of their HCF and LCM? What is HCF here? HCF is equal to 1, 2, 3 are consecutive numbers. HCF is equal to 1. And what is LCM of these three numbers? LCM is going to be 6. What is product of HCF and LCM? 1 into 6 is equal to 6. Now in this particular case, HCF into LCM is equal to product of three numbers. Now I would like to take some other numbers like 2, 3, 4. Right? So what is the product of these numbers? Product is going to be 2 3s are 6, 6 4s are 24 is the product of numbers. Correct? And what is HCF of these three numbers? HCF of 2, 3, 4 is only 1. Correct? And what is LCM of the numbers? LCM is going to be 2, 3, 4. When I find the LCM, 2 1s, 3, 2 2s are 4. Therefore, LCM is going to be 2 3s are 6, 6 2s are 12 is the LCM. What is product of HCF and LCM? 1 12s are 12. Okay. So, HCF into LCM is equal to 12. but product of numbers is equal to 24. So product of numbers is more than HCF into LCM. Product of numbers is equal to HCF into LCM. So what do you understand here? Product of three numbers should be more than or equal to HCF into LCM. So that you will have to write here more than or equal to the product of HCF and LCM. You understand? You can go with some other numbers also, then you will have to find out the logic behind the product of numbers as well as product of their HCF as well as LCM is going to be greater than or equal to. Right? So coming to the next one, that is if P is a prime number and it divides A square, then it also divides what? Actually, this is one of the statements in the proof of root 2 is irrational number, root 3 is irrational number, root 5 is irrational number. There, if P square is divisible by 2, then P is also divisible by 2. Have you remembered that statement? So similarly here also, P is a prime number and it divides A square. I am going to take one A square is a square number which is equal to some 25. Okay? What are the factors of 25? 5 and 1 are the factors of 25. Of course, 25 is also factor of 25. I would say that 5 divides 25. 5 divides 25 because 25 and 25 is divided by 5, it leaves the remainder 0. So when 5 divides 25, because 5 is a prime number, see here P is a prime number and divides A square. So 5 is a prime number, divides 25. Then it also divides. So 5 divides 25. What is the square root of 25? Square root of 25 is equal to 5. So 5 also divides 5, right? When 5 is divided by 5, it leaves the remainder 0. Therefore, if P is a prime number and it divides A square, then it also divides A, because 25 is divisible by 5. Square root of 25 is equal to 5 is also divisible by 5. So when A square is divisible by P, then A would also divisible by P. That is what is the answer. Coming to the next one, numbers having non-terminating, non-repeating decimal expansions are known as non-terminating, non-repeating decimal expansions. So these are part of rational non-terminating, non-repeating. Non-terminating, non-repeating means, are they a part of rational numbers? Absolutely no. For example, if I write a number 2.37162579631201 and so on. If you observe in this kind of non-terminating, it is not stopping anywhere, and non-repeating, there is no digit repeated or repeated pattern is not there. So this kind of numbers are particularly known as irrational decimal expansions. They are called irrational numbers. So if they are rational numbers, definitely the decimal expansion should be either terminating or non-terminating but repeating. Then those kind of decimal expansions are said to be rational numbers. But here, non-terminating, non-repeating, it is nothing but neither a terminating decimal and nor a repeating decimal. So these kind of decimal expansions are known as irrational numbers. What do you call the numbers? Irrational numbers. And these are irrational numbers. If any decimal expansion is either a terminating or non-terminating but repeating, then those decimal expansions are said to be rational numbers. But these are irrational numbers. So coming to the next one, write one rational and one irrational lying between 0.25 and 0.32. Okay. Now I am going to write one rational number. One rational number, see there are infinitely many number of rational numbers between any two rational numbers. It should be, the number should be more than 0.25, less than 0.32. I would like to write 0.26. Is this 0.26 more than 0.25? Absolutely. And 0.26 is less than 0.32? Yes. So this is one rational number. So rational number between them is 0.26. And I would like to write one irrational number between 0.25 and 0.32. What do you mean by irrational number? Just now we discussed. It's a neither terminating nor a repeating decimal. It should be more than 0.25. I would like to write 0.26, 1392, and so on. See, this is a number which is more than 0.25 and less than 0.32, but it is not a terminating decimal, not a repeating decimal. So my irrational numbers between them is 0.26, 0.261392 and so on. There are no repeated pattern. So that is why it is an irrational number. You understand? It is very easy to write a rational and irrational between the given two numbers. Every real number is either a dash number or dash number. What is this dash number and dash number? Real numbers can be divided into two categories. They are rational numbers and irrational numbers. In these rational numbers we have different types of numbers. What are those? Natural numbers, whole numbers, integers, together called as rational numbers. And irrational numbers are the numbers which are not rational is said to be irrational. Therefore, real numbers are divided into two categories. They are rational rational and irrational. You understand? Or you can consider that rational, irrational numbers together constitute real numbers. Therefore, numbers are rational numbers and irrational numbers. Coming to the next one, root 2, root 3, root 7, etc. are what kind of numbers? See, these numbers are not in the form of p by q, where q is not equal to 0 and p, q are integers. Therefore, these kind of numbers are said to be irrational numbers. What kind of numbers? Irrational numbers. And what is the HCF of the smallest prime number? What is the smallest prime number? 1 is not a prime number. 2 is the smallest prime number and which is an even prime also. So the smallest prime number is going to be 2. And the smallest composite number. So what is the smallest composite number? After 1 to 3 is also a prime number. 4 is the composite and which is the smallest. It is 4. Now you are going to find what is the HCF of these two numbers. So HCF of 2, 4. So these two numbers can be divisible by 2. Right? So there is only number 2 which is the common for 2 and 4. Therefore the HCF of the smallest prime number and the smallest composite number is 2. You understand? So this is about the problems given, multiple choice questions or objective questions, whatever it is, we discussed already. So please be focused on these kind of problems. Then definitely all these problems are pretty much easier, if I am not wrong. So please be very careful in order to understanding the problem and analyzing the situation. Then definitely you can score good marks. Hope you understand, enjoy the class. Thank you.